All right. Welcome to United Astronomy Clubs of New Jersey. We are here in Jenny Jump State Forest in Hope, New Jersey. And just to give people who are just pulling in a chance to park and find a bench or set up their chair, I do want to welcome not only everyone who is joining us here in the forest, but also online, because that is right, we do live stream these to both Twitch and YouTube. Great place to check out is our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, our past talks with links to see them, because we do keep them saved, as well as information on our member clubs, because that is right, we are actually an organization made up of other astronomy clubs, and one of the easiest ways to get involved in astronomy or any really any interest is to find and join your local club. So I do encourage you to go check them out. We have links to their website as well. You can also follow us on our social media channels, our Facebook, Instagram. We have a Discord server. They're great places to know what we're doing, as well as ask questions, whether it be, hey, I took a picture of this and it happened to be a SpaceX rocket from Cape Canaveral, or just like, hey, look at the cool aurora photos I got on my vacation. We'd love to see them. So it looks like we are slowly making our way down, getting settled here. Like I said, we do live stream these to both Twitch and YouTube, so if you're ever looking for something to do on a Saturday night at 8 p.m., feel free to join us. Hit those like, follow, subscribe, depending on which platform you're in. It does help us offer these to more people and get the word out there. So, first off, we're going to do a safety briefing here. If anyone needs to use the restroom, that is the porta potty in back. It is big. It is now green. It is illuminated by red for ease of finding in the dark. We also have a little museum and gift shop area, also to my left, but behind me. And the doorway to that is encircled with red. I will be manning that after the presentation, because they still won't allow me to break the laws of physics and be in two places at once. That is strictly not allowed. Speaking of it getting dark, we are in a state forest. It does get dark. It is quite overcast, so it will get extra dark. So we ask that when we go to leave, we are using our headlights because no one wants to be poor Frogger underneath the wheels of your car. And let's face it, no one needs those medical bills nor paperwork to fill out. That being said, if we need flashlights or any sort of light to get around, I do ask we try and keep those pointed towards the ground, because it's no fun being blinded by Amazon's latest greatest 100,000 lumen advertised monstrosity. Been there, done that, will not recommend. Each of the sheds you saw when you were parking houses its own telescope. On a normal night, where we can actually see the stars and clouds, because unfortunately visual telescopes cannot in fact see through clouds, we would have them open, or one or more of them open, and a volunteer manning them, so you would be able to have a look through those telescopes. I don't know whether we have anyone tonight who would be able to open up a shed to at least show you one of the telescopes, but Jaime has also set up his astrophotography rig, so at least you can see. We do, in fact, have telescopes here. With that, you're not here to listen to me ramble on or accidentally set off the speaker by being slightly too close. You're here to listen to Jaime Rodriguez. Jaime is a proud retired U.S. Army paratrooper with combat service in Afghanistan, 2 overseas tours in Germany, and 1 overseas tour in Hawaii, and various stateside assignments. He retired from active duty at Fort Carson, Colorado in the summer of 2016, and Jaime then joined the United States Department of Veteran Affairs, where he processed disability compensation claims for his fellow disabled veterans. He retired from that role in the summer of 2023 and took up astrophotography 3 years ago, and has served as one of our team leaders as well as an observer here at the Jenny Jump Observatory. And with that, I leave this to Jaime to teach us about astrophotography.
Hello, everyone, and thank you for being here. So tonight's presentation will be on astrophotography, and it's going to come up here on one of the first screens here. So let's get started. That's an introduction to astrophotography using both one-shot color cameras and monochrome cameras. So what is astrophotography? Astrophotography is the specialized art and science of photographing astronomical objects, celestial objects, and phenomena in large areas of the night sky. So how does astrophotography differ from visual astronomy? In visual astronomy, you're kind of just looking through an eyepiece to see what you're going to see right there on the spot. But just note that that's not always like a live view, because the light from the objects that you're looking at takes time to reach us here on the planet Earth. All right, so unlike, this is what I was just talking about. Unlike visual astronomy, astrophotography is actually, sorry, a few fun facts here. All right, I talked about how light takes time to reach us here on the planet Earth. So if you look, when you look at the sun, you're actually, and the sun, by the way, is actually a star. When you're looking at the sun, you're actually seeing it as it appeared 8 minutes ago, because that's how long it takes for that light to reach us here on the planet Earth. When you're looking at our nearest star, Proxima Centauri, other than our own star, the sun, that light takes 4 years to reach us here. But when if it's a clear night and you know where to look, you can actually see it. But that light has been traveling 4 years to reach you here on the planet Earth. Light from our nearest galaxy, the Andromeda galaxy, that takes 2.5 million years to reach us. But on a really, really clear night, if you're in a dark sky site, you'll see it as a little fuzzy patch up there in the sky. But it's 2.5 million light years away. All right. If we had a spaceship that could travel, that could blast off from the planet, or if at the speed of light, I'm sorry, which is 186,000 miles per second, um, our exit time depends on our direction of travel. So the fastest way would be either straight up or straight down from the center of the galaxy. That would take 500 years at the speed of light. If you're going to the nearest horizontal exit toward the rim, that would take 25,000 years just to leave our galaxy, the Milky Way galaxy. And the longest exit through the core to the far edge, that would take between 74,000 and 100,000 years. That's just to leave our Milky Way galaxy. That's just to give you an idea of how vast space is. So, what is a one-shot color camera? A one-shot color camera is a camera that captures a complete RGB image every time you take a picture. For example, a DSLR is a one-shot color camera. There are also dedicated one-shot color cameras for astrophotography. And so DSLRs are great for the budding astrophotographer, like when you're just getting started, um, as are smart telescopes, which we'll discuss a bit later. Another option, when you're ready, is a dedicated astrophotography one-shot color camera. And here on your screen are a few examples of what these things look like. In fact, I have one on my telescope there. And one of the big advantages of these one-shot color cameras is the ability to cool the main sensor. In fact, you can cool the sensor down to like minus 35 degrees of the ambient temperature. And the cooler the temperature is, the more crisp and the better data, the better image that you're going to get out of it. So if it's let's say it's 15 degrees out here, you can cool the the sensor down to like minus 20. And like I said, the more you can cool that sensor, the better your result is going to be. And then there's dedicated monochrome monochrome astrophotography cameras. So unlike color cameras, monochrome cameras capture all of the incoming light at each pixel, irrespective of color. Since red, green, and blue are all absorbed simultaneously, each pixel can receive up to 3 times the amount of light. This approach requires more work up front, but the results, not all the time, but the results usually exceed what you're going to get with a one-shot color camera, depending on how good you are at processing and how good was the data that you actually captured. And then finally, to complete a full color astrophotography image using a monochrome camera, we have to shoot through different filters. So in monochrome astrophotography, filters are essential because the sensor itself cannot distinguish color. You must take separate photos through different filters and combine them in post-processing to create a color image. And I'm going to show you guys a brief, like a 5-minute clip that shows how the folks that process the pictures for like the Hubble Space Telescope, the new one, the James Webb Space Telescope, it shows you how they do that process. So there are two types of filter sets used in monochrome astrophotography. They are referred to as SHOW, used for narrowband imaging, and LRGB, used for broadband imaging. SHOW, also known as the Hubble palette, SHOW imaging is a monochrome astrophotography technique that uses 3 narrowband filters to capture specific light emissions from ionized gases in space. These light emissions are in sulfur 2, that's going to be your red color, hydrogen alpha for green, and oxygen 3 for blue. And down in the bottom here, there are some pictures of different filter sets. All right, so narrowband filters explained. In layman's terms, the bandpass of a filter in narrowband imaging is simply the width of the window that a filter opens for light to come through. And here's a cool analogy that I found online. It's called the security gate analogy, how bandpass works. Think of bandpass as the amount of filter, as the amount of a filter, I'm sorry, as a security gate. The target, you only want to let in one specific guest, let's say hydrogen alpha, for example. The bandpass, this is how wide the gate opens. The narrow band pass, 3 nanometers. The gate is cracked open just enough for your guests to squeeze in. Almost all uninvited light, such as moonlight, street lights, and light pollution, is blocked out. This results in a very high contrast image with a dark background. Now, a wide bypass, like 7 nanometers or even 12 nanometers, the gate is wide open. Your guest gets in easily, but a lot of uninvited light pollution also gets in. Okay, now we'll talk about broadband imaging. LRGB or luminance red, green, and blue imaging is a monochrome astrophotography technique used to create true color images of galaxies, star clusters, and reflection nebula. It combines four distinct channels. Luminance, that's the clear filter that captures the total light that's coming in from your target. And then the red, green, and blue, these separate filters are used to capture the color data from the target that you're imaging. And here's a brief clip of how the folks at the Space Telescope Science Institute, the ones that process the Hubble images, the new James Webb Space Telescope images, and it kind of shows how they process these monochrome images.
How does this become this? Hi, I'm Joseph DePasquale,
And I'm Aletha Pagan.
and we're science visuals developers at the Space Telescope Science Institute, the Mission and Science Operations Center for NASA's James Webb Space Telescope.
Our job is essentially to take the raw images from Webb and extract and highlight the meaningful information by producing color images from the black and white data we receive.
So why do we do this? By composing color images from the data, we can see details that we wouldn't be able to see otherwise.
As science visual developers, this is what we specialize in and do every day, but it's something that you can do too. A great thing about the Webb Space Telescope is that its observations are available through the Institute's data archive called MAST. You can search for the data, download raw images from Webb, and try composing color images yourself.
In this series, we're going to break down the basics of how and why we take Webb's images from this to this. So follow along with us here and visit webbtelescope.org to dive deeper into the process of how Webb's full color images are made. You're looking at an image of thousands upon thousands of galaxies, billions of years old. This is what Webb images look like before image specialists process them to reveal their contents. Telescopes like Webb are designed with science in mind, and science goals are what drive Webb's observations. But to our great fortune, this instrument of science also captures the stunning beauty of the cosmos. Before I start working on a Webb image, the data have already gone through a lot. Scientists had to successfully propose to observe the target, which includes a lot of detail, like which filters Webb should use on its cameras. The data then went through a calibration system, developed primarily by scientists and engineers at STSCI, which corrects instrumental effects and extracts useful and accurate information. In order to begin composing color images from this data, we start by downloading the image files from our archive called MAST. Anyone, including you, can search for and download the files by using the target's name or coordinates on the sky. When we first open these images, they may appear black, but they actually contain a huge amount of information. Webb's detectors are so sensitive that they capture more light than our eyes or screens can process. So we need to use certain techniques to bring out the faintest details and make them visible to our eyes while preserving the brightest details. Stretching and compression are one of the ways that we do this. These techniques ensure we highlight the bulk of what was captured in the image. We then refine each piece of data by removing any artifacts or anomalies that might be hiding what's there. Downloading and working with the raw data in this way is exciting. It's kind of like getting a box of puzzle pieces without the picture on the box. And this is only the beginning of the process. Stay tuned for the next video in this series, where we'll dive deeper into the journey of composing color images from Webb data.
We're about halfway through this video.
While color images of space are incredibly gorgeous to look at, there are so many reasons behind our efforts to visualize Webb's data in color. There are many wavelengths of light around us every day that we can't actually see. The Webb Space Telescope sees infrared light, which is a type of light that's invisible to our eye. If you wore sophisticated infrared goggles and flew through space, you'd see the universe similar to how Webb does. But since our eyes can't naturally see in infrared, to see what Webb sees, we need to translate the light into visible color. Webb captures multiple images using different filters that detect specific elements or molecules. Then we combine those images to make a composite, assigning different colors to individual images based on the wavelength of light they detect. Just like you would translate a language you don't understand into one that you do, assigning colors this way helps us process the information in a way our eyes can understand. The words are always there, but now we can understand what they're saying. After translating the infrared data to visible color, it's time to consider the aesthetics. We use principles of photography to emphasize certain details and ensure that the image is visually engaging while we work with scientists to ensure we're maintaining the integrity of the original data. Composition is also a big part of this process. Sometimes this just means rotating the image to draw the eye to important info, and sometimes this means cropping images to create a more balanced look. There's no up in space, so our team gets to essentially decide what up looks like for each image we release. Composing color images from Webb's infrared data is a really unique combination of science and art. Similar to composing a symphony, we're carefully balancing each note or each color and scientific detail to create a harmonious, scientifically meaningful, and visually stunning view of the universe.
Webb has two main cameras, NIRCam, the near-infrared camera, and MIRI, the mid-infrared instrument. NIRCam captures shorter wavelengths of infrared light, while MIRI captures longer wavelengths. NIRCam has 29 filters, while MIRI has 9 filters. There are a large number of filter combinations that can appear in a Webb image. We assign colors in chromatic order, blue, green, red, from shortest to longest wavelengths for both of Webb's cameras. We then carefully review what each image contains and decide which filters to keep in the final composite image based on the data quality, science, and overall look. We'll create images from each camera, but we'll often have the opportunity to combine images from both cameras, which can produce stunning results. So there you have it, a brief overview of composing color images from Webb Space Telescope data.
Don't forget, this is all something you can try yourself. You can download raw images from Webb right now and try your hand at assigning color.
This series took us through the highlights, and you can learn more about the actual tools you'll need and the whole process through the resources and info on webtelescope.org.
Thanks for joining us on this colorful journey.
Okay, so a final note on filters. So note that the filters can also be used with one-shot color cameras. If, for example, you're imaging a target that emits both the hydrogen alpha and oxygen 3 wavelengths, like the Orion Nebula, for example, in this case, you can use a dual band filter like the Optolong L Ultimate to allow both the HA and O3 wavelengths to pass through and block everything else. There are even such things as tri-band filters and quad band filters as well. Oh, sorry. Okay, so let's start talking about entry-level telescopes. Smart telescopes are all-in-one automated imaging systems that replace the traditional eyepiece with digital sensors and a smartphone app. Unlike classical telescopes that require manual alignment and focus, these devices use internal computers to handle the complex steps of astrophotography. And as you can see there are some examples of, these are 3 most popular ones that are out right now: the ZWO C-Star Pro, S30 Pro, the S50, and then the Dwarf Lab 3. The key reason why these are beginner friendly: plate salving. The telescope takes a picture of the sky, recognizes the stars, and automatically censors your target. Live stacking. It captures and processes image in real time so you can see your color image on your screen within minutes rather than hours. And the longer you stay on that target, the more developed that image will become. And portability. These are all-in-one units that don't require external batteries, laptop connections, or lots of cables. And here's a few samples of images taken with the different smart telescopes. Guide cameras. All right. So in addition to your main telescope, and I can't get over there because I'm supposed to stay on camera. Maybe my assistant. Are you there, Al? Yeah. So a guide camera In addition to your main telescope, you need a smaller scope with a guide camera in it, and that's going to help your telescope stay on target all night long. It basically finds a good guide star, and once it's locked into that guide star, as your target moves across the sky through the night, that guide scope is going to keep that main scope centered right on your target as it moves through the sky at night. And here's a sample of a few different guide cameras. So that blue one, that's a guide camera, so is the red one. And then the two items on the right here are both guide scopes, as I have on top of my system there. But guiding is very, very important. If you're doing really short exposures, 10, 20 seconds, you can get by without guiding, which is also sometimes referred to as auto guiding. But if you want to do long exposure photography for those deep sky objects, you're going to need to do maybe 5-minute exposures, and for that you have to have guiding. If not, your stars will become elongated or egg-shaped. In fact, there's some samples here, and I don't know how much you guys can see. Actually, it's on my next screen. I'm sorry. Here's some samples of bad stars on the left. These stars appear elongated. The ones in the middle are kind of egg-shaped. And the one on the right, that's the best resolution image I can find. But actually, the blue background on this slide, it's the best sample of what your stars should look like. You want nice, beautiful, pinpoint stars when you're doing your astrophotography session. And for that, again, you need to be guiding. So why do we need long exposures? In astrophotography, we need to use long exposures because there is so little light in the night sky. The objects that we are trying to image are often very faint and far, far away. So we need to maximize the amount of light that reaches the camera's sensor. The benefit of this is that with long exposures, the camera's sensor can gain far greater detail than even the human eye. This is why many astrophotography images seem to capture more stars than you've ever seen with your naked eye, as in the following image of the Pac-Man Nebula. So here's a shot I took of the Pac-Man Nebula, and you can see how many stars are really there. Now, there's tools out there to either minimize or completely remove the stars. It depends, some people prefer to hold true to what the image really, really looks like, but I say beauty is in the eyes of the beholder. And here's an example here of a target I shot called the Heart Nebula. The one on the left has all of the stars in it. The one on the right, I removed the stars. Anybody have does anybody like one more than the other? Okay. So let's keep going. The composition of an astrophotography image. Astrophotography images are made up of at least 4 layers. These are the light layer, and then calibration frames. The light layer is obviously the light coming from your target. And we refer to the other 3 layers as calibration frames. They consist of dark frames, bias frames, and flat frames. We refer to all of these frames combined as data, as they make up the digital data that is eventually uploaded into a computer for processing. After capturing the light from coming from our target, we then capture the calibration frames. The dark frames are captured by putting the lens cap back on the front of the telescope, and you take a bunch of images that match the exposure length of your light frames and the same temperature. And then the bias frames are done the same way with the lens cover on, but these are really, really short, and they're not temperature dependent, or they're very fast, like 0.01 seconds. And then the flat frames, those are taken by putting picture the telescope facing straight up. You put like a white t-shirt over it, maybe secure it with rubber band, and then put a light pad on it. That's the old way. Now, hey Al, use this for a sec. Press this one to open it, and then that one to turn it on. So you have to be standing behind it. Now due to automation, there's easier ways of doing the light frames. I'm sorry, the flat frames. All right, once it's open, press the other button. So this is what I mean by shining a bright light into the telescope. That bright light, obviously we're going to close it now, but leave the light on. So when we're capturing the flat frames, this is exactly what we want. We want a bright light shining right into the telescope. And these exposures are really quick. I usually do like maybe 20, 25 of them, and they're also really fast. But you must have these in order to get your final image. Go ahead and open it and turn it off, Al. Because if not, sometimes if you have, let's say, little dust particles or little dust bunnies in your image, the flat frames will take care of that. When you stack everything together, you won't see it in your final result. Okay, the composition of an astrophotography image continue. Once you've uploaded all of your data, we use programs like PixInsight, Cirro, Deep Sky Stacker to stack all of these frames together into a single file. We then use either Cirro, PixInsight, or Adobe Photoshop to process these files into our final image. So looking from left to right, you have your light frames, your flat frames, your dark frames, your bias frames. That results in a final, it outputs a file that's ready for processing. And when you first start, just like in the video, this is what it looks like. So can any of you guys see the Orion Nebula there? Probably not. But once you process it, you start doing a process, it's called stretching, and then doing all the other processes, then at the end of the day, you'll get your final result. And that's the Orion Nebula. But when you first start, when I first started and I saw this, I thought I had just wasted 3 hours because I was like, where's my image? But then, eventually I found out how to bring it out. Okay, so let's talk about light pollution. Light pollution is the #1 adversary of all astrophotographers, even astronomers. Unless you're into astrophotography or astronomy, you wouldn't believe just how many consecutive nights can go by without one night that's suitable for this hobby. So in addition to checking for clear weather, clear nighttime weather, we also consider how light polluted our imaging site is. For this, we refer to the Bortle scale. The Bortle scale is a 9-level numeric system that used to measure brightness in the night sky and quantify the impact of light pollution at a specific site. This is a funny fact, but it's true. Many hardcore astrophotographers, myself included, have been known to base major life decisions on the Bortle scale, like they're moving or buying a house. Before they consult their partner, they'll consult the Bortle scale and start looking for a house. So, in fact, my real estate agent, are you here, Patrick? No, he's not here. My real estate agent can attest. I think we looked at maybe 15, 16 houses before I finally found one that suits this hobby. So let's keep going. Automation. All right, so automation, technological progress in astrophotography allows users to automate, monitor, and control their imaging sessions remotely. So I imagine before I got into the hobby, if you were doing a session and you were all set up, you went inside to stay warm, but if you lost focus, you had to bundle back up, come back outside, and refocus your telescope. Now they have these things called electronic focusers. You have your phone on you, Al, so you can shine a light on it? Anyway, with the electronic focusers, that's what he's pointing to right there. You can stay inside your nice warm place and refocus your telescope without having to come back outside and bundle back up and fix it. Same goes for filter wheels. Remember we talked about the filters. The filters are put in something that's called a filter wheel, which in fact this one there, he's probably pointing it out to you now. That's the big black circular looking thing. I have 7 filters in there. So in the past, let's say you were shooting a show image, sulfur, hydrogen, alpha. You did 2 hours on the sulfur. You came back out, pulled out the sulfur filter, slipped in the hydrogen filter, do another 2 hours and come back. Well, now the filters all change. You can do it all remotely. You stay inside nice and warm. In fact, when you're first setting up your sessions to begin imaging, you could tell there's a mini PC on there. You could tell the mini PC, okay, shoot me 2 hours worth of sulfur, then switch over to the hydrogen alpha filter, refocus the system, give me 2 hours on that, switch over to the oxygen filter, quickly refocus again, and then give me 2 hours on that, all without having to come outside. So automation is a great thing. Like I said, it was already, just starting when I first got into the hobby, but I think about those guys, that started long before me, and I wonder how was it for them having to come out and refocus and do all this stuff, um, by hand. So in addition to the focuses, there's the filter wheels, there's camera angles adjusters, that's called the CAA. A camera angle adjuster, basically, let's say your target up in the sky is orientated this way, but you want to kind of image it like that. So if you do it manually, there's a screw that you loosen, then you could physically rotate your camera so that the sensor is squared on the target the way you want it. Now they have these electronic rotators that I can just orientate that target the way I want it and get that perfect shot. So like I said, this is another thing that's automated. Before you would come, you would be out here moving your whole image train around till you kind of got it the way you like it, and then finally locking it in. Now you can do that remotely. Flat panels, we talked about the flat panels before. We showed you what that does. Uh, if you have an observatory, if you guys see these little white sheds out here, there's telescopes in there. These are observatories, and what we can slide the roof off so that the telescope can see the sky. Well, these days they have remote devices that you can just slide that roof off remotely. You don't have to go out there at night and slide that thing open, and at the end of the night slide it back. In fact, talking about observatories, what's really becoming popular now are remote observatories. These are places usually out west, because they have better sky conditions and all that. Whereas you can see in some of these images here, you can take your telescope out there, they set it all up for you, they plug it in, and then from your house, you come back east, wherever you live at, and you just log into your computer and you can do your imaging sessions from here while your telescope is way out there in Texas. The advantages are, we talked about the Bortle scale. So if you live in a Bortle 9, for example, forget it, you're in downtown Manhattan, super bright, very light polluted. If you're out there, out west, New Mexico, Arizona, they have like Bortle 1 skies. I don't know if you guys ever been out there and looked at the night sky, but you can see everything, the Milky Way galaxy, everything. So that's where some of these places are. There's one, the really popular one lately that just opened up maybe a year and a half ago is the Starfront Observatories out in Rockwood, Texas. But there are several, and I think there may be one or two here on the East Coast. I think maybe in Pennsylvania, but the darkest they get is maybe Bortle 3. And out here at some of these places, like I said, these are Bortle 1, Bortle 2. They average up to 200 clear nights per year. Here in New Jersey, we may get 60 usable nights per year for this hobby. All right, so getting started in astrophotography. Other than the dedicated astrophotography camera or DSLR, the 3 items that you definitely need to start with are definitely the telescope itself, the mount. They call it a mount because that's what you mount your telescope onto, and then a sturdy tripod. So DSLRs with shorter focal lengths and faster focal ratios, digital cameras are a good choice for capturing wide field images covering a large portion of the sky. We'll quickly talk about focal length and focal ratio. The focal length is like the magnification. So the higher the focal length, the more magnification you get on whatever you're imaging. And the focal ratio is how fast that imaging train, how fast your telescope can capture light. So if you have an f2, if your telescope is like f2 focal ratio, it's going to capture light a whole lot faster than a telescope that's like a f10 or f11. So that's the difference between focal length and focal ratio. Now, if you're imaging really far deep sky, faint, small, deep sky objects, you want greater focal length. I have something that's called the Edge 11. It has a focal length of 2,800 millimeters. And then, but the trade-off is that the focal ratio on that is like f11. So it's super slow at capturing light. So you have no choice but to do those really long exposures. So moving on, telescopes with a mid-range focal length and focal ratios are also a good choice for capturing stunning wide field images with more magnification. And lastly, oh, and there's a telescope I was telling about. That's the biggest one that I have. Large telescopes with high focal lengths offer a lot more magnification and are a good choice for deep sky objects as well as planetary and lunar imaging. The trade-off is, as I said, that the slower focal ratio, meaning that they're much slower at gathering light. So other than the telescope, next we'll talk about the mount. Again, the mount is the part that the telescope is mounted on. And as mounts go, all right, the mount is the part of the telescope onto which you mount the part of the astrophotography rig onto which you mount your telescope or DSLR. One of the most important characteristics is to consider when you're choosing your mount is the payload capacity. The more weight a mount can handle, the larger the telescope you can mount on it. So this would be like an entry level mount right here, and it's alt azimuth. This is by a company called Skywatcher. It's good if you're just starting off in the hobby, but another good choice are those really small telescopes that I showed you guys a few slides ago. That's another good choice if you're looking to start with. They're the ones that were called smart telescopes. Then next up would be something like a German equatorial mount. They're also known as EQ mounts. And then after that, you have the latest, greatest, the harmonic drive or strain wave gear mounts. These are also EQ mounts. When you look at these strain wave or harmonic drive mounts, I have one there. Best way to explain how these things are, if you can picture an automobile assembly plant where you see the robots, putting the cars together and all that stuff. These use that same technology. So something that's so small, you wouldn't believe how much weight this thing can handle. I mean, that's the biggest difference and between the older German equatorial type and now the newer harmonic drive mounts is the payload capacity in a smaller package. Because the one in the middle, that thing is so heavy and so big. This thing here, you can see how small it is, but I can put my big telescope on there with no problem. Then, okay, so we talked about the alt-az mode. So alt-az is basically altitude and azimuth. A good choice for the budding astrophotographer. And alt-azimuth mount is a simple two-axis mount for supporting and rotating an instrument about two perpendicular axes, one vertical and the other one horizontal. These mounts have several advantages when used for astronomical telescopes. Ease of use, portability, compactness, and the go-to feature. A go-to feature is like basically once you're polar lined, and we'll talk about that, you know what target you want, you punch in the catalog number for that code and it'll go to it. It'll move and go there. And so important note about these alt-az mounts, they're not ideal for deep sky astrophotography or prolonged astronomical observing because they can't follow astronomical objects as the Earth rotates. For deep sky astrophotography or prolonged astronomical observing, equatorial mounts are generally considered superior. And this next slide will tell you why. So unlike alt-az mounts, EQ mounts are ideal for deep sky imaging or prolonged astronomical observing because they can follow astronomical objects as the Earth rotates. Once polar lined, equatorial mounts are able to keep a specific target in your field of view without drifting away. This is because the mount has one axis that is driven at a constant speed parallel to the Earth's axis of rotation to compensate for the Earth's rotation. This arrangement is called a sidereal drive or clock drive. And now we talked a little bit about the harmonic drive mounts, but here it talks about the advantages, or how they differ from some of these older mounts. Position is one of the main things. The gear system allows for smooth, accurate movement, which is ideal for tracking celestial objects. Compact size, you guys can see this thing is not very big at all. Durability and reliability, harmonic drive mounts experience less wear and tear over time, so they are less likely to need maintenance and repairs. High torque, harmonic drive mounts can handle high torque in a compact design, which can reduce the need for a counterweight. So in this setup I have here, I put a counterweight on here just so that you guys can see what a counterweight is. But for that small telescope, I mean for that light telescope, compared to my bigger telescope, I didn't really need that counterweight. I just did it so you guys could see what it would look like with a counterweight on there. And then lastly, a smooth operation. The harmonic drive operates with a smooth continuous motion. Tripods. That's the last part of what you need for astrophotography, imaging rig. The tripod, these are kind of self-explanatory. The Skywatcher EQ, the Alt-Az tripod there. This one is the one on your left. I had one and I didn't feel very confident that it could really support a heavy load because they're kind of cheesy. But if you just like have maybe a camera on there, then you're okay. But you don't want to put a big heavy telescope on something that flimsy. Then you get a little more. You get into your carbon fiber tripods. These are popular. That's what this is. This is a carbon fiber tripod. Then you have the ones that are not just metal, but they're really thick. I mean, the legs are like maybe this big and round. Those will support really heavy telescopes. All right, conducting an imaging session. First, you want to start off by leveling your tripod. You can put a spirit level on there or bubble level. Make sure it's completely level, but very important that it's pointing toward the north, toward the North Star, or also known as Polaris. So you level your tripod facing north. Then you want to obtain like a rough focus. Get your initial focus. Then you'll do polar alignment. We're going to talk about that. Then you're going to slew. Slew just means pan or tilt to your target, and then refine your focus, and then you get going. So let's talk about focus first. Before you can attempt to polar align your mount, you must at least have a rough focus of your main telescope or DSLR. You can achieve this by using the focus knobs on a telescope. I don't know if you can see those because they're on this side, but there's focus knobs on there. But again, remember, I have the electronic focus on there. So those focus knobs are basically disabled because I focus electronically. Using a batten-off mask, I'll show you what that looks like. Let's see. Well, I'm not sure if you guys can see. I'll just pass it around. Can you pass it around? Actually, got this one. This one. Yeah, I'll put this back. Yeah. Anyway. So a batten-off mask is one way to do it. We talked about manually focusing, batten-off mask, and then using an electronic focuser, which I have on there. So let's show you what these look like. So batten-off mask is what Al is passing around now. And it was invented by an amateur Russian astronomer named Pavel Batinov. The Batinov focus mask works by diffracting incoming light into a predictable and recognizable pattern, which we can then use as a guide to perfect focus. So in this next part of the slide here, all right, so on your right side there, if you look at this shot, these two different shots taken with the batten-off mask in front of the telescope, the one on your left, that top vertical line is kind of skewed off to the right, so it's out of focus. You know that you're in focus when the three lines line up perfectly like that with the center vertical line right in the middle. That's when you know that you're perfectly focused, and you're looking at a star when you're using the batten-off mask. But that's kind of the manual way of doing it, the kind of old school way of doing it. Now, like I said, most people are using the electronic focusers. And there's a picture of the electronic focuser that I use that's on my telescope. All right, so polar alignment. I talked about how important that is. Put it this way, if you don't start your night with a good polar alignment, the rest of the night is just gonna not work out for you. You got to get a good polar alignment. And what it is you want to get your telescope perfectly pointed at the North Star, Polaris. And the way to find it, there's several different ways to find it, but if you look at the Big Dipper, also known as Ursa Major, The bottom star, let me see if I can point it out to you guys. That bottom star that's called Dubby, some people pronounce it Doobie, that one always points to Polaris. And if you're looking at the Little Dipper or Ursa Minor, the last star that's called Yulden, that one also always points at Polaris. And as the year goes on, the different these constellations appear in different places, but they always point to the same place. So I'll show you what I mean. Oh, in fact, if we come back here, you'll notice that a lot of these stars have Arabic sounding names, and I was curious to find out why that is. So this screen talks about that. Roughly two-thirds of all named stars in the night sky have Arabic origins. The reason is due to a monumental scientific movement known as the Islamic Golden Age, the 8th to the 14th century CE. During the European Middle Ages, while astronomical studies slowed down in the West, Islamic scholars across the Middle East, North Africa, and Spain became the world's leading centers of mathematics and astronomy. Something I didn't know. Interesting. All right, here's another way that you can find it. Like I said, during the summer, again, you look for W, and W will always point to the North Star, no matter. And then you see it in the spring. You just find that one star. Oh, I'm not attached to anything. You find this one star, whether it's there, or there, it's always going to point right toward Polaris. And if the sky clears up, I'll show you guys tonight. All right, so in this app that I use, or the Little Mini PC has an app that's here. Can you take it to the main app page on the tablet? Just go to the main page. I think I have the mount highlighted. Yeah. So this app here is called the ASI Air app, and this is what I use for polar alignment. There's other ways. There's other programs out there. Something that's called Nina. Something else called ShopCap. I like ASI Air app. I can use it right on my tablet or from my cell phone instead of having to use a laptop. So when you first start polar alignment, it takes the first picture and it does something that's called plate solving, where it's trying to recognize what part of the sky it's looking at. Then it'll rotate like 60 degrees, and then it'll start cueing you. Okay, just can you point to the two knobs for polar alignment? Yeah, it'll tell you adjust your knobs. It's basically trying to tell you, okay, move it a little left, okay, up, down. You keep loosening these, tightening that until, as you're watching the app on the screen, it'll tell you when you're getting close. And then finally, when you're on point there, you get a little smiley face, as shown here, that lets you know that you're polar aligned. Now, some people, like in this case, I think I came within 0.029 arc seconds. Some people will keep going till they get that down to 0. But as long as you have the smiley face, you're good to go. I mean, that's just the way I look at it. All right, so once we're polar aligned, at this point you would move to your target, move the telescope to your target and refine your focus, because you're about to get started. Make sure your focus is, in fact, there's a setting in there that I can tell it, okay, I'm ready, but before we get started, let's do one last focus before we start our session. Yeah. Then you want to turn on your guiding. Remember, we talked about guiding and how important guiding is. Get your guiding going and go into your plan and tell, okay, I want you to take 50 pictures of this, make it 3 minutes each, and then maybe switch over to this target, give me 50 pictures of that, make it 3 or 4 minutes each, and then finally you will start your session. So ways to get started, join an astronomy club. That's how I started. When I first started this hobby, actually when I first thought about starting this hobby, I was in Afghanistan, and I looked up at the night sky and I said to myself, if I make it out of here, I'm going to buy myself a telescope someday. And I did. But this is the funny part. I was so clueless before I joined the club that I was trying to do polar alignment in my living room. I didn't know. I just didn't know. And then I found out about this club, and I came out here and I met some really good people, and I found my mentor here, a guy named Mike. Mike took me under his wings, and before you knew it, I was doing what I'm doing now. So, but anyway, the best way to get started is to join a club. Start small. these can get really expensive really fast. Part of the mistake I made, I kind of went overboard, but I kind of grew into it, you know, something like this. But start small, like maybe the smart telescopes we looked at, or something like an alt-az, you know, start small, and then as you start to get better at capturing the data and processing it, you may start to consider getting something with a little more magnification. And then attend star parties. How many people know what star parties are? Raise your hand. Yeah, star parties, you can look them up online. There's this really big one out in Pennsylvania that's twice a year, I think it is. It's called the Cherry Spring Star Party. And you just go out there and you just picture a field, a big field with just hundreds and hundreds of telescopes and tents and trailers, and people just spend like 3 or 4 nights out there, and the people interacting, and you get to meet other people, learn other stuff from other people. So star parties are a lot of fun. So now we'll have a video montage of everything that I've done so far since I started. Well, all of the images that I've done since I started in the hobby. And I hope this thing plays. Let's see. I think it's going to work. What? Oh, I see. I see. Sorry about that. Yeah. The PowerPoint? Okay, I see. Maybe. Let's try this. Right click. Close all windows. Don't save. Okay, let's try that again. Take it back to the beginning. All right, try it again. Okay, sorry about that, folks. That's our neighbor we talked about, 2.5 million 2.5 million years away from Earth. Some of these I included Greek mythology on some of these. Not all of the targets have it, but some of them do. And the date that I captured the data. We saw this earlier. This is the Orion Nebula. I think next will be the Horsehead Nebula. If you look closely, it kind of looks like a horse's head there. The Heart Nebula, I think that was in my presentation as well. That's they call it the Pelican Nebula. You can kind of see the beak and the eye there. It's supposed to resemble a pelican. Some of these, that's how you get their names, by what they kind of look like. This is, that big galaxy is swallowing up that little galaxy. It's called the Whirlpool Galaxy. This is a supernova remnant. That's what it looks like after a star blows up. That's what's left. I think this is the Ring Nebula. No, the Dumbbell Nebula. This is 3 galaxies in one frame. It's called Leo's Triplet. Most of what you see here, believe it or not, are galaxies, but it was hard for me to get a better resolution on this. But those blotches are all galaxies. That's the Fireworks Galaxy, yes. I think everybody knows what this one is. I took all these images were captured right here at Jenny Jump. Yeah. And the moon is actually doing video instead of photography. It's hard to explain, but you do it in video, then you program process it through different programs to get your final result. This is supposed to resemble a Christmas tree with the light up on top there. Anybody see a Christmas tree in there? That's the horse's head. It's called the Blue Horse Head Nebula. It's supposed to resemble the head of a horse. That's my furthest target ever. 290 million light years. It's called Stephan's Quintet. That's the famous Eagle Nebula with the pillars of creation. In this one, I removed the stars, most of the stars. This is the Rosette Nebula. I think it's also, no, it's an emission nebula, I'm sorry. That one's supposed to resemble the California coast, so they call it the California Nebula. This one to me looks like a lion's face, but it's called the Trifid Nebula. I see a lion when I look at that. What is this? Oh, it's a spiral galaxy. 10 million light years away. The Iris Nebula. The resolution on this looks a lot better when I look at it on my computer from when I look at it here. That's supposed to be a Viking's helmet. They call it Thor's helmet. And I had to really crop that one to get in on it. Rho Ophiuchi, it's a star cloud complex. The Seagull Nebula. Yeah. That looks to me like Yeti, but it's called the Ghost of Cassiopeia. It looks like Yeti. That looks like a buffalo to me, but it's called the Soul Nebula. Maybe a bison or buffalo. Anybody see that? The Seven Sisters, also known as Pleiades. It's a star cluster. And Home Sweet Home. I think you guys know what that one is. So that wraps up the presentation. I know Kim has got some other stuff to talk about.
All right. Thank you for another great presentation. So
You're
we
welcome.
are going to be doing a question and answer session. But before we get into that, I noticed a couple people had snuck in after the safety briefing. Just a reminder, anyone here who needs to use the bathroom, that is the porta potty in back. It is illuminated by red for ease of finding in the dark. We do have a museum and gift shop area. I'll be manning that after the Q&A session. It is still incredibly overcast. We do not currently have any telescopes open for viewing because of that. That being said, I don't know if I have anyone who can actually open a telescope and at least show you, hey, this is one of our telescopes. I will have to ask them after this. When we go to leave, we are using our headlights because it is dark and we prefer not to have people run over. It hurts when you get run over, so if you see cars moving, move out of the way. Also, because it is dark, if we need flashlights or whatnot to move around, I do ask we keep those pointed towards the ground. With that, how question and answer session is going to work for people here, you're going to raise your hand and wave it about like you just don't care. Keeping in mind, I'm like the Jurassic Park T-Rex. My vision at night is based on movement because I've been monitoring online chat and therefore have no night vision. So all of you are kind of shadowy figures in the dark. Online chat, you have it easy. You get to type your questions and I get to read them. So how this we're going to start this off with the first online question was, is there a temp that is actually too cold for the camera rig, or rather, how cold is too cold?
I've never had any problems, and I've been out here. Al can attest to this on really, really cold nights where the camera was probably cooled down to like minus 30, minus 25. Um, Maybe that's an exaggeration, maybe minus 25. And I never had any bad results or bad effects because of it on my final image. So I don't know what is too cold, but I've cooled some of my cameras down to like minus 25, no problem. Yeah.
And I would imagine it depends on what gear you're getting. I mean, we're operating cameras in space, which I can't think of too many places
Yeah.
colder than space.
Yeah.
But that's just me.
And not all astrophotography cameras are cool, are able to be cooled. Some of them, the ones that are called Pro, like let's say 6200 MC Pro, anything that ends with Pro is a cooled camera. You can cool it. Yeah.
All right. Any questions out here? Perfect.
Could you tell me how long are your exposures, and do you ever have exposures that span multiple nights?
The longest I usually am willing to push is 5 minutes. Um, but I'll capture, a lot of those. Um, I know there's some people I've seen YouTube videos where people doing like over several nights. Obviously you stop when the sun comes out, but over several nights they're doing 10-minute exposures for like several nights, and the results that they get are stunning. But I'm imagining they're in really beautiful dark skies that are not light polluted and with good weather, no wind, because even wind can affect your final image. You'll get elongated stars if it was very windy while you were setting up. Yeah, but to answer your question, the longest I do is 5 minutes. I know there's people out there that do 10 minutes, and I know there are people that do multiple nights on one target. Like they'll get, 6 hours tonight. If it's clear tomorrow night, they'll hit it again for another 6 hours. Unfortunately, here in New Jersey, we're not that fortunate to get that many clear nights in a row. Yeah.
Right. Oh, follow up.
I just want to follow up on that.
Yes.
Are your exposures just a single exposure over 5 minutes, or do you have multiple exposures that you stack on top of each other?
That's correct. I may do as many as 24 5-minute exposures with I think I'm pretty sure it equates to 2 hours. So I'll tell the little app, I mean the little mini PC, all right, go to this target. I want you to shoot 24 5-minute exposures. So that gets me 2 hours of data on just that one target. Yeah. Yeah. And sometimes if you have a telescope with a faster focal ratio, let's say something like f2, you can get the same amount of data in 1-minute exposures because it's capturing that light so much faster. But yeah, I average, with my big telescope, I'll do like 5-minute exposures. I've pushed it up to maybe 6 minutes on perfect nights, but that's so rare. Yeah. But the more data you get, the more of those long exposures you get, the more, the more information you're getting from that target. Well, the more data, the more light that's coming from it, the better your result is going to be when you finally process it.
Right. Our next online question. When using a monochrome camera and changing out filters, how do you tell the difference between them in the dark? And I think you've solved that problem by just having the automagical wheel of doom that changes them for you.
Yeah, Kim. Yeah, in the electronic filter wheel, when you first buy it, you got to kind of open it up. You screw all your filters in place, all 7 of them. You plug it back in, and then you go into the app and you tell them, okay, position number 1, I want that to be my luminance filter. Position number 2, I'm going to label that one R for, and then position 3 will be G, and then B, and then LA. So I just know if I tell the the system, hey, bring up the hydrogen alpha filter and give me 20 shots on this, it knows exactly what position, and the filter wheel will bring up that filter and put it right in front of the camera.
And I would imagine anyone doing this manually is very much in the this is where this filter lives and it shall only live there, sort of thing. Or I would imagine, barring that, little red light, flashlight goes a long way into reading labels.
Yeah.
All right, I see a question all the way in the back.
For your C11, do you shoot natively at 2800 millimeters, or do you have a reducer?
I've started with the reducer shooting at 1960 millimeters. Um, and then I was using the ZWO 2600 MC Duo. So it's a camera that has both the main sensor built in, but there's also a little guide sensor in there too. Um, I've struggled shooting at 2800 millimeters because I'm not that good at off-axis guiding. But I have shot at 2800 millimeters. Yes, to answer your question, I have.
All right, our next online question is, what is the shortest amount of time you usually need to set everything up and align everything to have the crispy pinpoint stars?
Oh, I wouldn't say. I mean, once your rig is, all set up, and all the cables are plugged in, and you're powered up, and you're looking toward the North Star
Yeah,
and
I think
everything.
they're talking from like you are literally plopping down from the start, plopping down the tripod.
I mean, it could take me. Well, don't forget, I like setting up during the daylight. I don't like waiting, coming out here when it's already nighttime. So I usually get here way before nightfall, and I'm completely set up. So that would probably take me 30 minutes, maybe a little bit less. Now, once nightfall comes, maybe 20 minutes once I'm polar lined and focused before I can start imaging. Yeah.
All right, so we're looking about 50 minutes total time.
Split up between
yeah.
how early I get here and then before nightfall. Because you can set up, but then you can't do anything till the sky turns dark.
But it's a lot nicer setting up when you can see all the little
That's
ports.
why I come early.
All right, what's there another question out here? I hear a lot of crickets, I think. I was told the other night, no, those are katydids. And I'm like, I don't know, but they live here. All right. Online people, do get your questions in. This is just a reminder because by the time you hear this, we're already a minute or so into the future.
Hello, YouTube world.
Let's see. The next question is, has Jaime considered doing one of the remote rigs in locations like Texas or whatever?
I actually am thinking of taking a telescope out there, and I'm trying to time it where if I do make the drive out there to Texas, I like the one that's called Starfront Observatory. I want to time it so that the same weekend as the Formula One Grand Prix of Austin, Texas. So I have to work out the logistics. But yes, the answer is yes. I do want to take one of my telescopes out to one of those remote observatories because then I'll get to image maybe 200 nights per year as opposed to 60 nights per year here in New Jersey.
You just you want to multitask so that you're only spending the gas to get down there once.
Yeah.
Right. Question. Bueller. Oh, not as many people know that movie. Apparently,
Ferris Bueller's Day Off.
Yeah. Right. So our next online question is, how often do you have trouble with the automations not doing the things and having to go out and do the stuff manually anyway?
Not often at all. Once everything is properly plugged in and everything is properly aligned, the most glitch that you may have, that we typically have during a regular night of imaging, sometimes for some reason our guiding numbers will just go plop where you're looking. Good guiding numbers are anything below 1. So like 0.05, that's really good guiding. 0.79, that's great. Once you start getting about 1.0 and higher, even 1.0 is okay, but I don't know, once you're up there like, I don't know, 2.3 or whatever, something's going on. Either it got windy or somebody bumped into your telescope, but you'll see it, and you'll see it in your guiding numbers. But yeah, the most common issue we may run into during the night of imaging is issues with guiding. Sometimes, that may arise. Never really issues with focusing because the electronic focuser does its job. So yeah, I would say guiding. Al, do you want to add anything to that? Yeah.
The consensus is guiding from our other astrophotographer in the audience. Right. Let's see. Questions? All right. So our next online question, and like I said, last call online people to get your questions in. I don't want to accidentally miss any of you. When you happen to ask the question after stream has ended. All right, so our next question is, does having that counterweight on the rig when it doesn't need the counterweight damage or cause problems with your gear?
No, no, because the mount is specifically designed to support this 22-pound counterweight. So like I said, I only have it on there tonight because I wanted the audience to see what it would look like if I did need it. But this mount can support, without a counterweight, 44 pounds. With the counterweight, it can support 66 pounds. This rig that I have on here right now may weigh 20 pounds, maybe altogether, everything.
So we can add one of the small children in the front row and still be
easily.
Good then. We are not actually going to add the small child to the telescope rig.
But to answer this question, no, it won't cause any harm to it because it's designed to handle it.
Yeah, but you just wouldn't run it like that though,
Mhm.
because you don't need that. Right. Last call for people out here. Any questions? He's probably gonna be around for a little bit because he has to break down his rig, and that takes a few minutes.
Oh yeah.
But I do want to thank everyone who is joined us.
I'm sorry. Before you go, if anybody wants to come up and get a closer look after she's finished, I'll stick around for a few minutes.
Yep. Thank you, Jaime, for another great
You're
talk.
welcome.
Hope to see you back here again. Well, I'll see you because there's team nights and whatnot.
Yes,
But
yeah.
like another talk.
All right.
Thank you, online people, for everyone who's not only chatted but also lurked. It does help us. Like I said, hit those like, follow, subscribe buttons. Anyone here, keep in mind if you're looking for something to do at 8 p.m. at a Saturday, we're always here. Say hi in chat. We love to ask and answer questions. Also, remember, check us out on our website, uacnj.org, for all that fun information you might be missing. With that, I want to thank everyone who's also donated and bought the special merch for our fundraiser for our we're hoping to break ground on a new observatory building to house our 25-inch telescope that we currently don't have on site, but we're looking. So everyone who has donated to that, we greatly appreciate that. With all that said, thank you, everyone. Clearer skies than we have right now, and good seeing. Have a great night.